This is a video lesson on combining trig functions. Often in applications we find a use for this. It's interesting that we can take a combination of sine and cosine functions. If we add them together, for example, a sine x plus b times cosine x, we can combine those as a single trig function. In this case we have, for sine, the formulas go like this. The amplitude of the combined function will be the square root of the sum of the squares of the coefficients on the left side. So the square of a, square of b, square root. This follows directly from Pythagorean theorem and using an addition formula for the sine function. The details of that are in your textbook, or you can just Google that. So finding the amplitude is actually very straightforward. We just sum the squares, square root. For finding the phase angle on the right, phi here is called the phase angle. And that's a little harder. What we have to watch out for mainly is quadrant. And that'll be determined by the signs, plus minus signs, of the two expressions down here at the bottom. It just so happens that the cosine of phi, that phase angle phi, will satisfy capital A over k, and the sine of phi will be b over k. And usually we're going to need a calculator to approximate the angle phi, being mindful about quadrants. Quadrants would be determined by the positive or negative of a and b. Let's run through a few examples to see how this works. Oh, one more thing. It's also fine to use this setup even if the multiplier on x is not 1. So for example, if we had sine 2x and cosine 2x, then we would have a 2x over here on the right. And that all works as long as both arguments have the same multiplier. So for example, if this was sine 2x and this was cosine of, say, 5 times x, then we wouldn't be able to use this. But if the multiplier is the same in both sine and cosine on the left, it'll be the same multiplier on the right. The other formulas remain the same. So starting off with, let's work with the easiest case, which is where our phase would lie in quadrant 1. So let's say we have 5 times the sine plus 12 cosine x. You might recognize 5 and 12 as being part of a perfect right triangle where we have integer values for our three sides. So we're going to try to figure out what k is, and then secondly, the phase angle phi. So it's just commented 5 and 12 make up a nice triangle, right triangle, where the hypotenuse would be 13. So our value for k is 13. It's the square root of 5 squared plus 12 squared. Okay, having determined k first, we can now write down the formulas for cosine and sine of our phase. So using the formulas, we've got cosine phi is a over k, which in this case would be, a is 5, so 5/13. And the sine of phi would be 12/13, b over k. Okay, at this point we need to use a calculator if we expect to approximate the value, which is typically what we'll do. I'm going to work in radian mode. If we take the cosine inverse or sine inverse of the appropriate number, we'll get a value for this. Okay, so sine inverse of, say, 12/13, that's approximately 1.1760. Now that's a quadrant 1 angle in radians, and that'll work for us. So we're done at this point. The final answer is that 5 times the sine of x plus 12 times the cosine of x is approximately, I'm going to use an approximation symbol since we're rounding that phase. It's approximately 13 sine of x plus 1.1760. Now that phase is not unique. We know because sine is periodic with period 2 pi, we could add any integer multiple of 2 pi to this phase and we would still be okay. To check your answer, one way to do that would be to use your graphing calculator, and on the left, for one of the functions, enter in the left side, so y1 would be 5 sine x plus 12 cosine x, and then below that in your y2, put in 13 sine of x plus 1.1760. Make sure you're in radian mode, and then graph them simultaneously, and you should see the same curve. If you see two distinct curves, you'll know that you've made an error. Typically the error will be in your phase. You'll see one wave shifted off from the other. For the second and third examples, let's look at what happens when we have a sign change in here. So let's start with negative 5 sine x plus 12 cosine x. So we're looking at the same setup. The only difference is we've changed the capital A from plus 5 to negative 5. Now that will not have an effect on our amplitude K, but it will definitely affect our phase angle phi. Again, that's the most common error when students work with these kind of combination problems, is they don't adjust their calculator answer by the quadrant. So still, we've got K is 13. It's going to be the same because it's going to be the square root of negative 5 squared, which of course is still 25, and 12 squared, so 13. And as pointed out several times now, the difference will be, you have to slow down here on finding your phase. So in this case, the cosine is negative 5/13, and the sine of phi is positive 12/13. Now, before jumping in and grabbing a calculator, let's think about what quadrant we should expect this angle phi. If the cosine is negative and the sine is positive, that puts us in quadrant 2. And we've got some choices here. We can use the sine inverse of 12/13 to start, and then we would have to adjust that angle, because the calculator is going to give you, we already know what it'll give us the same angle that we got in the previous example, which was 1.1760 radians. That's in quadrant 1. But we want the quadrant 2 angle. So our angle is over here, or any coterminal angle with that quadrant 2 angle phi. Okay, so the easiest way to do this specific example would be to use the inverse cosine, and that follows from the fact that the cosine inverse function, the inverse cosine function, its range is in quadrants 1 and 2. So if we were to use the cosine inverse of negative 5/13, that'll do it for us. Had we used the sine inverse of positive 12/13, we would have gotten this angle over in quadrant 1, and then we would have to subtract that angle from pi to get this angle. So that's another way to do it. Okay, cosine inverse of negative 5/13 is approximately 1.9656. Okay, that makes sense. That's a quadrant 2 angle. That's beyond half of pi, which is about 1.57. Pi is 3.14. Alternatively, we could have done pi minus the sine inverse of 12/13. This is a kind of computation that you've got to get good at as a trig when applying trig, as it happens nearly every time we need to work with a calculator and finding inverse, approximating angles using inverse trig, in that we're not always going to be using what our calculator tells us. The calculator is not smart enough to determine quadrants. We have to follow through with adjustments that way. At this point we're done. We can use either one of these will give us the same value. If we had used pi minus sine inverse of 12/13, we'd get the same 1.9656. So we're done at this point. Our solution is that minus 5 sine plus 12 cosine x is going to be very close to 13 times the sine of x plus 1.9656. And once again, we could add any multiple of 2 pi to that, any integer multiple of 2 pi, and we'd be fine. As our final example, let's consider where both capital A and B are negative. And let's throw in a different multiplier on the inside. So let's say we've got negative 5 sine 3x minus 12 cosine 3x. This, once again, this will be an amplitude k times the sine. Now since these have 3x on the left, we'll need 3x on the right, plus some angle phi. So as long as you have the same multiplier on both expressions on the left, you use the same multiplier on the right. Had one of those 3x's been something different, like cosine of 5x, then this formula would not work. Well, I hope by now you recognize that the amplitude k will still be 13 since we're summing the squares, and squaring preserves signs. So k is still 13. Square root of 5 squared plus 12 squared. And when working with our formulas, we have the cosine of phi will be negative 5/13, that's a over b, and sine phi will be negative 12/13. Now to test yourself, you may want to pause this video and then on your own use a calculator to determine that angle phi approximately. Let's round to 4 places in radian mode. First thing I like to do is determine a quadrant. These two signs, both negative, tell me that phi is in quadrant 3. And your calculator will not give that to you directly. When using the inverse sine and inverse cosine functions, your calculator will give you either an angle. In the case of cosine inverse, it's going to give you a quadrant 2 angle, and in the case of sine inverse, it's going to report a negative angle in quadrant 4. Let's go ahead and use that one. So let's say I took the sine inverse of negative 12/13. And if we do that, our calculator is going to give us a value of negative 1.1760. So the calculator is giving us this angle down here, as it should, because we're working with a negative sign, a negative sign would be either quadrant 3 or quadrant 4, but your calculator only reports in the range of the inverse sign, which is in quadrants, is minus pi over 2 to pi over 2, so quadrants 1 and 4. Okay, so that's the angle given, negative 1.1760, but we want the equivalent angle in quadrant 3, so the angle we really want is over here. And so to do that, it's not that difficult. You just got to be careful, slow down, make sure you get this right. We're going to take that 1.1760, think of that as the angle over on this side, and add pi to it. So don't write that phi equals sine inverse negative 12/13 because it's not equal to it. Phi, sorry, phi will be equal to pi plus 1.1760. And since we're approximating, we'll put a approximation symbol there. And with using our calculator, this comes out to 4.3176. And now we're done. So negative 5 sine 3x minus 12 cosine 3x. It's just about the same as 13 times the sine of 3x plus 4.3176. So with the exception of finding phi and adjustments to quadrants, trust those formulas. They work pretty well for you. In my class, you don't need to memorize those. You can write those, or they're provided for you on a formula sheet during exams. I hope this helps. Thanks for listening.